Hi everyone, my name is Nindhia with the student ID number ending in 080. Today I will be talking about Chapter 7, Polymers, Structure, General Properties, and their application. First and foremost, this is the outline of the topics described in Chapter 7. We'll discuss about polymers. They are one of the most widely used materials in modern manufacturing, competing directly with metals and ceramics in many engineering fields. We'll discuss how their molecular structure affects performance. There are various types such as thermoplastics, thermostats, and elastometers, and finally where and why they're used in the industry. Polymers are long-chain molecules formed by linking smaller molecules called monomers through a process known as polymerization. They can either be natural, such as cellulose and rubber, or synthetic, such as bakelite and polyethylene. Compared to metals, polymers offer significant advantages. They are lighter, cheaper, and resistant to corrosion and chemical attack. Their ability to reduce noise and their high formability makes them excellent for applications where weight and flexibility matter, such as automotive interiors and consumer goods. However, polymers also have limitations. They generally have low strength and stiffness, limited surface temperature, around 350 Celsius maximum, and poor dimensional stability under heat or load. Despite this, their benefits and easy processability makes them crucial materials in modern engineering and manufacturing. This is the advantages that polymers have compared to metals. This table shows the range of mechanical properties for various engineering plastics at room temperature. This data helps us understand how different polymers compare in terms of strength, stiffness, flexibility, and deformation characteristics. The second column shows ultimate tensile strength, UTS, a measure of how much stress the material can withstand before breaking. The values range widely from as low as 7 MPa for materials like polyethylene and fluorocarbons, and up to over 1,000 MPa for reinforced epoxies. This enormous variation demonstrates how additives and reinforcement like glass fibers or carbon fibers can transform a weak plastic into a high-performance engineering material. The next column lists Young's modulus, which measures stiffness or rigidity. For example, ABS has a modulus of about 1.4 to 2.8 GPa, while reinforced epoxies can reach as high as 52 GPa. This again shows how structural reinforcement significantly increases stiffness and load-bearing capacity. The elongation column, the percentage, shows how much a material can stretch before breaking. This indicates ductility or flexibility. Finally, the Poisson's ratio on the very right represents the ratio of lateral strain to axial strain. In simpler terms, how much the material contracts in the lateral direction when it's stretched. The structure of a polymer determines most of its mechanical, thermal, and chemical properties. At the molecular level, polymers can be thought of as a chain of repeating units called mers that are connected end to end. There are two key types of polymerization reaction. The first being addition polymerization, where monomers join without producing any byproducts such as polyethylene, and condensation polymerization, where a small byproduct like water or methanol is released. Nylon is a typical example. Polymers can have several structural configurations. First being linear polymers. Like PVC and nylon, they have straight chain and can be flexible. Branch polymers have side chain that lower their density and personality. And the last being cross-linked and network structure from rigid three-dimensional frameworks typical of thermosetting plastics like epoxies and phenolics. Depending on the number of monomers used, we classify them as homopolymers, one type of monomer, or copolymers, which indicates two or more. The structural variation allows engineers to tailor properties for specific uses, from flexible films to strong structural composites. Now in figure 4.2, we can see the different structure of molecular of various polymers. The first being polyethylene, second polypropylene, the third PVC, the fourth polystyrene, and the fifth being a Teflon. Now let's look more closely at polymerization, the fundamental process of forming polymers. Polymerization is the chemical reaction in which small monomer molecules link together to form long-chain polymers. There are two major types of polymerization, the first being condensation polymerization. This is a step growth reaction where each step releases a small byproduct, such as water or methanol. A good example is the formation of nylon 6.6, produced from adipolyl chloride and hexamethylene diamine. Each reaction between monomers produces a byproduct molecule, forming a long, strong chain. The second being addition polymerization. In this chain growth reaction, monomers join together without any byproduct. It usually requires an initiator, like a free radical or catalyst, that starts the reaction by opening a double bond in the monomer. A simple example is the polymerization of ethylene to form polyethylene. Now this over here is an example of for A, it is an example of nylon 6.6, produced from adipolyl chloride and hexamethyl diamine. We can see how those two link together to make nylon 6.6. And then B is the addition polymerization of polyethylene molecules from ethylenemers. An important measure here is the degree of polymerization, dP, which tells us how many repeating units a polymer chain contains. The equation being dP equals molecular weight of polymers by molecular weight of repeating unit. A higher dP means higher molecular weight, which usually results in greater strength, viscosity, and toughness. Polymers also have two kinds of bonding: primary or covalent bonds along the chain that hold the backbone together, and secondary bonds like van der Waals and hydrogen bonds between chain, which affects flexibility, melting point, and processability. Overall, polymerization defines the polymer's mechanical behavior and thermal limits, setting the foundation for all of its applications. Now moving on to crystallinity. Crystallinity plays a major role in determining a polymer's mechanical and thermal behavior. Unlike metals, polymers are not completely crystalline. Instead, most are semi-crystalline, meaning they contain both crystalline and amorphous regions. In crystalline regions, called crystallites, the molecular chains are tightly packed and folded in an orderly arrangement. Meanwhile, in amorphous region, the chains are randomly oriented, giving flexibility. For example, high-density polyethylene, or HDPE, has a crystallinity of about 80 to 95%, making it strong and stiff. In contrast, low-density polyethylene, or LDPE, has a crystallinity of 60 to 70%, which makes them softer and more ductile. As crystallinity increases, several key properties improve. Stiffness, hardness, density, heat resistance, and solvent resistance all increases. However, ductility and rubber-like behavior decreases. Now to the left is an example of the HDPE versus LDPE, and on the right, figure 7.5 is a schematic illustration of polymer chain. The letter A, or the top on the left, is a linear structure. Thermoplastics such as acrylics, nylon, polyethylene, and polyphenol chloride have linear structure. The one next to it, branch structures such are seen in polyethylene. The one on the left, a cross-linkage structure. Many rubbers or elastomers have this structure. And lastly, on the right, D, the network structure is basically highly cross-linked. Examples are thermosetting plastics such as epoxies and phenolics. The degree of crystallinity depends on the polymer structure and cooling rate. Slow cooling allows the chain to align, producing a higher degree of crystallinity. Fast cooling prevents alignment, resulting in a more amorphous structure. Also, branching reduces crystallinity because side chains prevent the chain from packing closely together. For the optical properties, more crystallinity means more light scattering, which means it has an opaque appearance, where versus the fully amorphous polymers, for example acrylics, they are transparent. This is the continuation of the behavior of polymers as a function of temperature. And then for B, it's the degree of crystallinity and cross-linking, the combined elastics and viscous behavior of polymers. In short, controlling crystallinity is a key design factor. Engineers can balance strength and flexibility by adjusting processing conditions like cooling rate and molecular structures. Next, we'll discuss a very important concept, the glass transition temperature, or TG. TG is the temperature at which an amorphous polymers change from a hard glassy solid to a soft rubbery state. This is another example of the amorphous and crystalline regions in polymers. There we can see the amorphous regions, and then we can see the crystalline regions, which seem more uniform. Below TG, or transition temperature, the polymer molecular chains are frozen, it's stiff and brittle. Versus above TG, the chains gain mobility, allowing the material to bend and deform easily. This transition isn't a sharp melting point like in metals, rather it's a gradual change that occurs over a temperature range. The glass transition is mainly relevant to amorphous and semi-crystalline polymers because fully crystalline materials have a distinct melting point, Tm. We can identify TG experimentally from a specific volume first temperature curve, where a noticeable change in slope indicates the transition, as shown as in figure 7.9 in the book. Here are some common examples, where polystyrene, the TG is somewhere around 100 Celsius. For PVC, it's somewhere around 87 Celsius. PMMA, somewhere around 105 Celsius. Polycarbonate, around the same as PMMA. And rubber is negative 73 Celsius. The difference between TG and TM is also worth remembering. Amorphous polymers only have TG, no sharp melting. Semi-crystalline polymers have both TG and TM. They soften gradually and then melt suddenly at higher temperature. In practice, TG is critical for engineers. It determines the surface temperature of a polymer. If used before TG, a material will be rigid, good for housing, containers, or lenses. Above TG, it becomes flexible or rubbery, used for seals, films, or coatings. So, controlling TG through material selection and additives allow designers to ensure that a polymer performs properly under specific temperature conditions. This figure shows how the specific volume of polymers changes as temperature increases. On the vertical axis, we have specific volumes. That's essentially how much space the polymers occupies per unit mass. On the horizontal axis, we have temperature. The graph includes two curves, one for amorphous polymers, such as acrylics, and one for partly crystalline polymers, such as nylon. As we heat an amorphous polymer, it expands gradually until it reaches a point called the glass transition temperature, TG. As we said before, below TG, the polymer behaves like hard brittle glass. The molecular chains are frozen and can move freely. But once the temperature rises above Tg, the polymer becomes soft and rubbery because the molecular chains start to move and slide past one another. That's why you can think of Tg as the temperature range where a polymer changes from rigid to flexible. It's not a sharp melting point, but rather a gradual transformation in molecular mobility. Now this right here, table 7.2, is the glass transitioning and melting temperature of some of the polymers. Now let's talk about polymer blends, a strategy engineers use to combine the strength of multiple polymers in one material. A polymer blend is simply a mixture of two or more polymers that are physically combined, not chemically bonded, to achieve specific property enhancements. This is similar to how metals are alloyed to create new mechanical properties. The main purpose of blending is to improve toughness, impact strength, and ductility, especially for brittle amorphous polymers that might otherwise crack under stress. One of the most common examples is ABS plastic, acrylonate, butadiene, styrene. In ABS, a small amount of rubber, butadiene, is dispersed in a hard plastic matrix, allowing it to absorb impact energy and resisting crack, perfect for helmets, car bumpers, and tool housing. Blends can be two main types. Miscible blend, polymers mixed uniformly, forming a single homogeneous phase with smooth properties, and immiscible blends. The components remain separate but still improve overall performance, for example by combining flexibility and rigidity. Polymer blends account for nearly 20% of total polymers production today and are widely used in automotive, electrical, and consumer applications because they're cost-effective and highly customizable. To sum up, polymer blending is a practical, flexible approach that allows engineers to design materials with tailored performance, without having to develop entirely new polymers from scratch. 7.3 talks about thermoplastics, one of the two major categories of synthetic polymers. Thermoplastics are polymers that soften when heated and harden when cold, a reversible process. Their molecular chains are linear or branched. Together, they are held by secondary bonds that weaken upon heating and reform upon cooling. This property allows thermoplastics to be melted, shaped, and reprocessed multiple times, making them highly recyclable and easy to form into complex geometries. Their key characteristics include toughness and flexibility, low density and good chemical resistance, impact resistance, but limited surface temperature, typically below 350 Celsius. Examples of common thermoplastics include ABS, they are tough and impact resistant, used for helmets and housing. Nylon, which is self-lubricating and strong, they are used in gears and bearings. Polycarbonate, they are transparent and high strength, used for safety lenses and shields. PVC, they can be rigid or flexible, used in pipes and electrical insulation. Polyethylene, such as LDPE, HDPE, and UHMWPE, used for bottles, films, and artificial joints. Acrylic, they are high optical clarity, used in windows and display. And finally, PTEE or Teflon, they are exceptional chemical and heat resistance. They are used in seals and cookware. So here is figure 7.10, and we'll begin with that one, which compares the stress-strain behavior of three categories of plastic. There is rigid and brittle plastics, such as filament. There is tough and ductile plastics, such as ABS and nylon, and there is soft and flexible plastics, such as Teflon. On the x-axis, we have strain, the amount of deformation, and on the y-axis, we have stress, the applied load. Notice how rigid and brittle materials show high strength but low strain. They can withstand a large load, but they break suddenly without much deformation, very similar to how ceramics behave. These are typically thermosetting plastics, which are hard and dimensionally stable but not flexible. Next, the tough and ductile materials such as ABS and nylon exhibit a broad stress-strain curve. They can absorb a lot of energy before failure, showing both strength and elasticity. This makes them ideal for impact-resistant parts like automotive bumpers or tool housing. Finally, the soft and flexible plastics like polyethylene and Teflon show low strength but high elongation. They can deform substantially without breaking, making them perfect for films, bags, and flexible tubing. So this figure helps us visualize the wide range of mechanical behaviors that polymers can exhibit, from brittle to rubber-like, all depending on molecular structure and bonding. Moving on to the middle one, figure 7.11, which is the effects of temperature on the stress-strain curve. In this case, this figure shows the temperature effects of the stress-strain curve of a polymer, in this case the cellulose acetate. At the temperature around -225 Celsius, the polymers behave brittle and strong. The stress-strain curve rises sharply but fractures quickly with very little elongation. This happens because the polymer chains are frozen. They can't move or slip past each other. As the temperature increases to around 0 or 25 Celsius, the polymer begins to show more ductility. It stretches more before breaking, and the stress peak decreases. At an even higher temperature, 50 Celsius to 80 Celsius, the polymer becomes soft and rubbery, showing large deformation but very low strength. This pattern demonstrates a critical concept. As temperature rises, strength decreases but ductility increases. Essentially, the polymer transitions from a glassy rigid state to a rubbery flexible state as it passes through or near its TG. Lastly, on the very right, figure 7.12 shows the effect of temperature on the impact strength of various plastic. The x-axis represents temperature and the y-axis shows impact strength, which is a measure of how much energy the material can absorb before breaking under sudden load. Here we can see that most plastics, including low-density polyethylene and PVC, shows a sharp drop in impact strength at low temperature. This is known as the ductile to brittle transition. At temperatures below TG, the polymer chains can't move freely, so the material becomes brittle and fractures easily when struck. As temperature increases above TG, chain mobility improves and the material becomes tougher and more impact resistant. This over here is an example of a stress elongation curve for polycarbonate, which is a thermoplastic. This figure illustrates how thermoplastics behave under tensile loading, specifically polycarbonate in the stress elongation curve. Shown on the left, and high-density polyethylene in the specimen photo on the right. So for the stress elongation curve for polycarbonate, in the graph, the horizontal axis shows elongation, or how much the specimen stretches under tension, and the vertical axis shows stress, the applied load per unit area. At the start of the test, there's a linear region where stress and strain are proportional. This corresponds to the elastic region, where the formation is fully recoverable if the load is removed. Next, we observe a yield point, where the polymer begins to deform plastically. Beyond this point, molecular chains start to uncoil and align in the direction of the applied stress. The figure labels this as molecules being oriented. This molecular orientation is a key characteristic of thermoplastics under tension. As the chain align, the material temporarily weakens, stress decreases slightly, but then as stretching continues, the oriented structure begins to resist further deformation, causing the stress to rise again. This phenomenon is known as strain hardening or cold drawing. So even though the polymer initially yields, the increasing alignment of molecules actually strengthens it as it elongates. This is why polycarbonates and other tough thermoplastics can undergo large uniform elongation before failure. They can stretch several 100% of their original length without snapping. Moving on to B, the tensile test specimen. On the right of the figure, you can see the tensile specimen of a high-density polyethylene after testing. Notice the long narrow region in the middle of the sample. This is where the material has necked and elongate uniformly. In metals, necking typically localizes and leads to immediate fracture, but in polymers, the neck can propagate along the specimen's length as the material continues to deform. This behavior demonstrates how plastic flow and chain orientation distributes deformation over a larger region. This combination of neck formation and molecular arrangement gives thermoplastics their characteristic ductility, allowing them to absorb large amounts of energy before breaking. Now let's discuss the second major category of polymers, thermosetting plastics, also called thermosets. Unlike thermoplastics, which soften and can be reshaped repeatedly when heated, thermosetting plastics undergo a permanent chemical change when cured. During this curing process, the polymer chains form strong three-dimensional crosslinks, resulting in a rigid and infusible structure. Once a thermoset is hardened, it cannot be remelted or reshaped. Heating it again will only cause it to burn or decompose, not soften. This irreversible reaction is what gives thermostats their high-strength dimensional stability and resistance to heat and chemicals. Examples of common thermostats include epoxies, unsaturated polyesters, and silicone. These materials are typically formed by compression molding, transfer molding, or reaction injecting molding, followed by curing through the heat or catalyst. The structure of thermostats is characterized by a network of covalent crosslinks connecting the polymer chains. This cross-linking restricts molecular motion, resulting in a hard, brittle, and strong solid. Because of this structure, thermoets have high rigidity and hardness, excellent dimensional stability even at elevated temperatures, outstanding resistance to deformation, creep, and solvents, and also poor ductility. They can fracture under impact or bending. Think of thermostats as the metal equivalent of polymers. They are not flexible but strong and stable. They are ideal for structural parts, adhesive, coating, and electrical insulation. However, the main disadvantages is their non-recyclability. Once cured, the material cannot be reprocessed, which limits sustainability compared to thermoplastics. Now let's discuss additives, which play a crucial role in tailoring polymer properties for specific applications. When polymers are produced, they are rarely used in their pure form. To improve performance, various additives are incorporated into the polymer matrix, either to enhance mechanical strength, durability, color, or processing behavior. Some of the main type of additives include fillers. They add materials like calcium carbonate, talc, or glass fibers to increase stiffness, reduce cost, and improve dimensional stability. Plasticizers increases flexibility and reduces brittleness by lowering the glass transition temperature. Stabilizers protect polymers from degrading due to heat, UV light, or oxidation. Colorants, they add pigments or dyes for appearance. Lubricants and processing aids, they improve mold flow and reduce friction during extrusion or molding. And lastly, flame retardants prevent ignition or slow combustion in plastics used in electronics or constructions. By carefully selecting additives, engineers can design polymers that perform optimally for their intended use. For example, UV-resistant PVC for outdoor pipes or fire-retardant ABS for electronics. Let's also consider some examples of how additives modify polymer behavior. So for example, adding plasticizer to PVC, it transforms it from a hard, rigid pipe material into a soft and flexible cable insulation. Now let's look at section 7.6, General Properties and Applications of Thermoplastics. This section covers the general properties and applications of thermoplastics. So thermoplastics are by far one of the most common types of polymer used in manufacturing today. Everything from packaging films to structural components. Their popularity comes from a unique combination of lightweight, toughness, and recyclability, which makes them extremely versatile for engineering and consumer applications. First, let's go through their main properties one by one. Low density or lightweight parts. Thermoplastics are typically much lighter than metals, only about 1/5 to 1/6 the density of steel or aluminum. This makes them ideal for reducing product weight, improving fuel efficiency, and lowering transportation costs. That's why industries like automotive and aerospace increasingly use polymers to replace heavier metal components. Good strength to weight ratio. While they aren't as strong as metal in absolute terms, their strength relative to weight is quite high. When reinforced with glass or carbon fibers, thermoplastics can achieve metal-like performance with a fraction of the mass. Excellent corrosion and chemical resistance. One of the biggest advantages of polymer is their ability to resist corrosion and oxidation. They don't rust, and most are unaffected by water, salts, and many chemicals, which is why materials like PVC and polyethylene are used in piping and chemical containers. Low electrical and thermal conductivity, good insulators. Thermoplastics are naturally excellent insulators, both electrically and thermally. That makes them perfect for electrical components, cable coatings, and thermal barriers. Wide range of stiffness and toughness depending on polymer types and additives. By modifying the structure or adding reinforcements, engineers can adjust properties dramatically, from soft, flexible materials like LDPE to hard, tough ones like ABS or nylon. Additives, fillers, and bending can fine-tune these properties to meet specific design requirements. Next, dimensional stability lower than metals. Creep under load at high temperature. However, thermoplastics do have limitations. Because their molecular chains can side over time, they are more prone to creep, that is gradual deformation under constant load, especially when exposed to heat. This is why polymers are typically used in moderate temperature environments below their TG or melting temperatures. Melting. Most thermoplastics melt or soften below 350 Celsius, making them easy to shape and process using methods like injection molding, extrusion, and thermoforming. However, this also limits their use in high temperature applications where metals or ceramics would perform better. One of the key benefits of thermoplastics is that they can be melted, reshaped, and reused multiple times without major degradation. This recyclability gives them a strong advantage over thermosets, which permanently harden once cured. They are virtually everywhere, from household goods to high-performance engineering parts. In the automotive industry, they're used for bumpers, dashboard, and fuel tanks because they reduce the vehicle's weight and improve efficiency. In packaging, polymers like polyethylene and polypropylene are ideal for films, bottles, and containers due to their flexibility and transparency. In electrical and electronics, thermoplastics such as PVC are used as insulator, housing, and connectors. In medical devices, biocompatible plastics like PTFE and polypropylene are used in tubing, syringes, and implants. And in construction, PVC and acrylics are used for pipes, panels, and window glazing due to their durability and weather resistance. Essentially, thermoplastics combine formability, low cost, and adaptability. qualities that make them indispensable in nearly every sector of modern manufacturing. This is their performance enhancement. So to summarize, thermoplastics are lightweight, corrosion-resistant, and easily moldable materials. They offer a wide range of mechanical and thermal properties depending on structure and additives. While they have lower temperature resistance and creep under load, their recyclability and processability makes them ideal for mass production. In short, thermoplastic represents the most flexible and economically valuable class of polymers used in today's engineering world. Thermosetting plastics behave quite differently from thermoplastics. While thermoplastics soften repeatedly when heated and can be reshaped, thermostats undergo a permanent chemical reaction during their initial curing. Let's look more closely at their key properties. First, permanently hard and rigid. Once a thermostat is formed and cured, its molecular chains are locked together through extensive cross-linking. These covalent bond form a three-dimensional network, giving the material its characteristic stiffness and hardness. Because of this cross-linkage structure, thermostats maintain their shape even at elevated temperature. They don't soften like thermoplastics. Instead, they retain rigidity up to around 300 Celsius or more, depending on their formulation. That's why they're commonly used in high-temperature electrical and structural components. Cross-linkage also provides superior mechanical strength and creep resistance, even under load or heat. Thermostats resist deformation, which is crucial in applications like circuit boards or composite panels. Thermostats are very resistant to solvent, acids, and corrosions. They exhibit excellent electrical insulation properties, making them ideal for switches, sockets, and encapsulated electronic parts. On the downside, thermostats are brittle. Once cured, they cannot absorb the large amount of impact energy or deformation before curing. That's why they're used where stiffness and heat tolerance are more important than flexibility. Because of the permanent cross-linkage, once a thermostat is hardened, it cannot be reprocessed. This makes them less sustainable compared to thermoplastics, though they can still be grounded and reused as fillers in some cases. Here are some of the most common thermosetting plastics and their real-world uses. So the first, phenolics or bakelite, the first synthetic plastic ever made. It is excellent electrical insulators and heat resistance. It's used for electrical switches, handles, knobs, and household appliances. Next, epoxies. They are known for outstanding adhesion, chemical resistance, and dimensional stability. Used as adhesive coatings, encapsulants, and composite matrices in aerospace and automotive components. Next, polyesters or unsaturated polyester resins, often reinforced with fiberglass to form fiberglass reinforced plastics (FRP), widely used in boat hulls, car bodies, and construction panels. Urea formaldehyde and melamine formaldehyde, used in laminates, tableware, and decorative surface due to hardness, heat resistance, and glossy finish. Silicone, unique for their thermal stability and flexible at high temperatures, used for seals, gaskets, cooking coatings, and medical devices. And lastly, polymerides, high temperature resistant thermostats used in electrical, aerospace, and insulating films. Each of these highlight how thermostats are chosen based on their performance under stress, heat, or chemicals is more critical than recyclability or flexibility. Moving on to 7.8, biodegradable plastics. Traditional plastics can take hundreds of years to decompose in the environment. To address this problem, scientists evolved biodegradable plastics which are designed to break down naturally through the action of microorganisms such as bacteria, fungi, or algae. These microorganisms convert the polymers into water, carbon dioxide, methane, and biomass, depending on environmental conditions. The goal is to reduce plastic waste and create materials that can safely integrate into the natural ecosystem after use. So what exactly are biodegradable plastics? They are polymer capable of decomposing under natural conditions, typically when exposed to moisture, oxygen, and microbial activity. The degradation process involves two main stages, the first being depolymerization, which microbes or environmental factors break the long polymer chains into smaller molecules. And second, assimilation. Microorganisms consume these small fragments as food, converting them into CO2, water, and biomass. The rate of degradation depends on first temperature. Higher temperature accelerate breakdown. Moisture, microbes require water to thrive, and polymer composition, amorphous or unless crystalline materials degrade faster. However, it's important to remember that biodegradation occurs efficiently only under specific composting conditions. For example, in industrial composite facilities where heat and humidity are controlled. Biodegradable plastics can come from natural or synthetic sources. Naturally derived polymers, these are made from renewable biological materials such as starch, cellulose, or acetate. Starch-based plastics, common in food packaging and agricultural films, and cellulose-based plastics, they are derived from plant fibers used in films and coatings. Next, synthetic biodegradable polymers are man-made polymers designed to degrade naturally. Examples include PLA or polylactic acid. They are made from cornstarch or sugarcane used in packaging, 3D printing, and biomedical implants. There is also PHA, produced by bacteria, used in packaging and medical applications. And there is also polycaprolactone or PCL and polybutylene succinate PBS, which is petroleum derived but fully biodegradable under composting conditions. Each type offers different mechanical and thermal properties, allowing engineers to select materials that balance strength, flexibility, and degradability. Biodegradable plastics often have properties similar to conventional plastics, but with added environmental benefits. They are lightweight and flexible, lower thermal resistance, so they are unsuitable for high temperature use. Hydrophilic, which means water absorbing, which helps biodegradation but can limit long-term performance, and can be composted, breaking down completely under the right condition within months. However, in natural environments like oceans or landfills, where oxygen and moisture are limited, degradation is much slower. That's why biodegradable plastic should ideally be collected and processed in composting facilities, not thrown away with regular waste. Despite their advantages, biodegradable plastics still face several major challenges, such as higher costs. Production often involves fermentation or specialized raw materials, which increases price compared to petroleum-based plastics. There are performance limitations. Over strength and heat resistance can restrict use in structural or long-term applications. Composting infrastructures. Effective biodegradation requires controlled environments, which are not always available in every country. And lastly, publicly misunderstood. Some people assume biodegradable means it can safely litter anywhere, but in reality, most types still require industrial composting to fully break down. So this is the degradation process and the properties, as I said before. The degradation process are heavily influenced by temperature, moisture, and polymer composition. And these are the applications. For packaging, it can be for bags, bottle films, and disposable containers, replacing single-use plastics in food service and retail. For agriculture, mulch films that decompose after harvest, eliminating the need for cleanup. In medical field, biodegradable sutures, implants, and drug delivery system that safely dissolve in the body. And for consumer goods, compostable utensils, straws, and plates designed for single use. These applications focus on short-life products where durability is less important than environmental impact. Now we come to the last major class of polymers, which is elastomers, also commonly known as rubbers. Elastomers are unique because they can undergo extreme large elastic deformations, often stretching several times their original length, and still return to their original shape once the load is removed. This elasticity sets them apart from both thermoplastics and thermosets. In simple terms, Elastometers combine the flexibility of a fluid with the solid structure of a polymer. They play a critical role in modern engineering, used everywhere from tires and seals to vibration isolators and medical devices. To understand their behavior, let's look at the molecular structure of elastometers. Elastometers are composed of long, coiled polymer chains that are only lightly cross-linked. When no stress is applied, the chains are randomly oriented and entangled. When stretched, these chains uncoil and align in the direction of the stress, storing elastic energy. When the load is released, the cross links pull the chain back to the original coil configuration, giving the material its elastic recovery. This structure provides high extensibility, excellent resilience, and low stiffness compared to other polymers. If the cross-linking is too slow, the material behaves like viscous liquid. If it's too high, it becomes rugged and brittle. So, the degree of cross-linking must be carefully controlled to balance elasticity and strength. Elastomers have several distinct properties that make them irreplaceable in engineering applications. First, they are extremely high elasticity. They can stretch up to 1,000% strain and recover completely. They deform easily under small loads, making them ideal for absorbing shock and vibration. They can repeatedly deform and return to shape with minimal energy lost. Some can operate from negative 100 Celsius to 300 Celsius depending on the material. They have low strength and stiffness compared to plastics and metals. Therefore, they are not used for load-bearing structures but for flexibility and sealing functions. They are also good resistance to impact, abrasion, and fatigue. These properties depend heavily on the molecular structure, fluid content, and cross-linking density. Next, elastomers are divided into natural and synthetic categories. So for the natural rubber and R, they are derived from the latest sap of rubber trees. It has excellent elasticity and resilience, but limited resistance to oil, sunlight, and ozone. They are used in tires, seals, and vibration isolators. Next, synthetic rubbers. The first one is the neoprene. They resist to oil, water, and ozone, used in hoses, and belts. Natural rubber or NBR, excellent oil and fuel resistance, used in gaskets, seals, and fuel hoses. Oatly rubber or IR, very low gas permeability, used in inner tubes and liners. Silicone rubbers or SIR retain flexibility from negative 100 Celsius to more or less 300 Celsius, used in medical tubing, seals, and bakeware. Lastly, PU polyethylene, high absorption resistance and strength. They are used in rollers, wheels, and coatings. Each elastomer has its own specialty. Engineers choose them based on environmental exposure, temperature, and mechanical needs. Elastomers are used widely in both industrial and consumer products due to their flexible and durability. In essence, elastomers complete the polymer family. Thermoplastics offer flexibility and recyclability. Thermostats provide rigidity and heat resistance, and elastomers deliver unmatched electricity and energy absorption. To wrap up, elastomers are highly elastic polymers capable of large reversible deformations. Their lightly cross-linkage molecular structures provide flexibility and resilience. Vulcanization enhancements mechanical and thermal stability, transforming raw rubber into a tough, versatile engineering materials. Common elastomers include natural rubber, neoprene, natural, butylene, silicone, and polyurethane. They are widely used for sealing, damping, insulating, and vibration absorption in industries ranging from automotive to healthcare. I forgot to mention about vulcanization. It is one of the most important developments in elastomers technology is vulcanization. It is discovered by Charles Goodyear in 1839. Vulcanization involves heating natural rubber with sulfur, causing sulfur atoms to form cross-linkage between polymer chains. These covalent sulfur bridges significantly enhance the mechanical and thermal properties of rubber. As a result, vulcanized rubber becomes stronger and more elastic, more resistant to wear and deformation. They are less sticky and less sensitive to temperature changes. This process turned natural rubber from a weak, sticky material into one of the most valuable industrial materials, enabling applications like tires, seals, hoses, and belts. Modern elastomers may also be cross-linked using peroxide or radiation instead of sulfur, depending on performance requirements. On the graph, the vertical axis represents load, and the horizontal axis represents elongation, or the amount of stretch. You'll notice that there are two separate paths, one for loading, where the rubber is being stretched, and one for unloading, where the rubber is released. The curves do not overlap. Instead, they form a loop, which we call the hysteresis loop. This hysteresis loop is extremely important because it represents energy loss during each cycle of stretching and recovery. When the rubber is loaded, part of the mechanical energy applied is stored elastically, but part of it is converted into heat due to thermal friction within the polymer chains. So, as the rubber unloads, it doesn't return all the energy. The area enclosed by the loop shows the energy dissipation. This is what we refer to as the hysteresis loss. In simple terms, the rubber doesn't behave like perfect spring. It loses a bit of energy each time it's deformed. This behavior is not a flaw, it's actually one of the key functional properties of elastomers. That hysteresis allows rubbers to absorb and dissipate mechanical energy, which is extremely valuable in engineering. So in short, rubber's hysteresis is what makes it not just flexible but functional. It's the reason elastomers are critical in absorbing and managing energy in countless mechanical systems. It is caused by internal friction and viscoelasticity behavior of the polymer chains. That is all that I have to offer in this video. I deeply apologize for any mistakes that I've made or things of the sort. Thank you so much for watching, and I really appreciate it, and see you all next time. Bye!